electricity tariff for each location. Technologies to be implemented on the manufacturing plants. The availability length in the Gebeng is large and the price is almost 50% cheaper compared to the other sites. So Gebeng is the most strategic and suitable location due to its vicinity to potential marketing areas, abundant raw material supply, availability of labor, cheaper water tariff, and also attractive tax incentives.
Okay, so next is the process selection. So we have came up with 3 different reaction processes. The first one is the hydroformylation of propylene, which involves the reaction between the propylene with the syngas to produce N-butylaldehyde and also isobutylaldehyde. So at the same time, it also undergoes a side reaction in which supported vanadium oxide. Well, the third reaction is the isomerization of methyl alcohol. So this reaction involve the reaction between the methyl alcohol with the sulfuric acid to produce isobutylaldehyde, and it also can be further proceed with the hydration of the alcohol to form butene glycol and undergoes the hydration to form isobutylaldehyde. Okay, so next. Okay, we also have done the economic potential. So for the hydroformylation of propylene, with the EP is RM 21 ringgit to 21 ringgit and 20 cents per pound. While for the catalytic synthesis of isobutylaldehyde, the EP is 2 ringgit and 68 cents per pound. While for the third, next. Hello. 26 cents per pound. So the price of the raw materials and also the isobutylaldehyde, we get it from Alibaba.com. Okay, next is the advantages and disadvantages of each reaction path. So for the hydroformylation of propylene, the advantages is that it is largely used process in the chemical industry, and then the use of the rhodium complex catalyst will give a higher yield of isobutylaldehyde, which gives 90% of conversion and also 95% of selectivity of butylaldehyde. While for the second reaction, which is the catalytic synthesis, the catalyst used is proven to be an effective catalyst, which can form a high conversion of isobutylaldehyde and also a very high yield, around more than 60% of the product. While the third reaction, which is the isomerization of methyl alcohol, it will yield a pure form of isobutylaldehyde, which is almost 96% of yield. Okay, next, Amy. So for the disadvantages of this reaction path is the first one, for the hydroformylation of propylene, it we came out with the selection ranking table. So we have set the weightage for each parameters, and we have give the mark for each parameters considering the priorities of the factors. So the factors involved is the EP, the economic potential, the conversion, the selectivity, the environmental aspect, and also the reaction condition. So after a thorough evaluation that we have decided the best reaction path is the hydroformylation of propylene. as we can see from the table that it has the highest economic potential, highest conversions and selectivity. Also, it have a moderate reaction conditions. So the best reaction path for our plant is the hydroformylation of propylene. Okay, so next. Okay, so next is the process flow diagram. This is our process flow diagram. So in order which that propylene will form propane and the butyl aldehyde will form butanol, isobutanol and N-butanol. It then will goes to the flash drum V100. So here it will be divided into two-phase system, the vapor phase and the liquid phase. So considering the efficiency of the separation is 95%, and also the boiling point of each component, so 95% of the raw materials, which is the propylene, propane, the hydrogen, and the carbon monoxide, will live at the vapor phase at stream 9. So here, the propane will be removed from the system through the membrane separator. And this is because that we want to avoid the build-up of the inerts in our system, while the rest of the mixture will be recycled back to the system. So leaving the liquid outlet of the flash drum, which is stream 12, it will then be fed to the distillation column T101. So here the butyl aldehyde and the butanol will be separated. So leaving the bottom part of the distillation column will be the butanol isomers, and then this butanol isomer will undergo further separation at the distillation column T103, and it will be separated into N-butanol and also isobutanol. So for the butyl aldehyde, it will undergo separation at the distillation column of T102. So leaving the top part of the distillation column will be the isobutyl aldehyde, while leaving the bottom part of the distillation column will be the N-butanol. So our final product, which is isobutyl aldehyde, we get the mass flow rate of our product is 5,788.4 kilograms per hour. All right. So next, Amy. One thing, Mike.
Okay, boleh dengar?
Boleh.
Okay. So next we move on to our manual mass balance calculation. So as you all can see in the slide, here are some process hydroformylation of propylene process specification, such as the syngas to propylene excess ratio is in 1.1, and then propylene overall conversion is 90%, butana conversion to butanol is 12%, separator efficiency is 95%, and our feed is not pure propylene. It also consists of 1 mole percentage of propane, and propane have a selectivity of 5%, while butana that consists of isobutana and also N-butana have a selectivity of 95%. So we have 4 chemical reactions in our reactor, which is the first one, propylene will be react with syngas. There are hydrogen and carbon monoxide to produce isobutana and also N-butana. So the second reaction, which is a side reaction, the propylene will react with hydrogen to produce propane. And then both butana will undergo hydrogenation to form butanol. So here, the process specification here, we are referred to one of the journal. As you all can see, I have put the reference at below. And our basis of calculation is to produce 50 kMTA of isobutadiene. So we have changed it into kg per hour by considering our plant will be operate for 360 working days a year and 24 hours a day. So next. Okay, next we move on to the overall mass balance. So this is the overall mass balance table. As you all can see, we have eight component here, and each equation we have total up their stoichiometric ratio. Any
Why? Why one thing?
the slide?
Slide ada. Ada kan?
Ada
I-
slide
saya-
ada.
Saya like okay, sudah nampak. Okay. So from you can see after we total up the four chemical equations, then we get the total stoichiometric coefficient for each of the chemical components. So what's meant by this table is for every 2 mole of propylene consumed, we are able to produce 0.836 mole of I-butylaldehyde, which are our main product. So this is for the overall mass balance. While for the mass balance for each unit, we are using the extent of reaction method. Okay, next.
So as for the energy balance, for the manual energy balance calculation is done by using the heat of formation method, and the reference condition that is used is carbon solid, hydrogen gas, and oxygen gas at 25 degrees Celsius and 1 atm. And for the heat flow enthalpy, it's calculated by adding up heat of formation, and sensible heat. And heat of vaporization is included if there is any phase change. Properties used for the calculation are as shown in the table below. Next. So as you can see, for the process simulation, it's very much similar to what my friend has explained just now. So what I would like to highlight here is that the thermodynamic property that has been chosen to use for the process simulation, the universal quasi-chemical activity coefficient was model is used for the simulation of this process. This is because the model is very suitable for both polar and non-polar components. Next. So for the comparison of manual and Aspen for mass balance, there are 3 significant errors from the stream 9, 10, and 11. So this error is due to the incompatibility of separators that was used in the Aspen environment. Next.
Apa yang nampak energy punya ni?
Belum lagi. Okay, so for the comparison of manual and Aspen for energy balance, there are 8 streams with significant errors. And for streams 9, 10, and 11, I would say the errors are the ones that originated from the mass balance calculation itself. And for streams 7, 13, 14, 15, and 24, it is assumed that the error could have been due to the difference of reference condition that is used for manual calculation, and also the reference condition as in the Aspen environment. And also it could be due to the rate of vaporization that has been used in the manual calculation. Yeah. Next.
So last is the process innovation and modifications. On the left side is the conventional process that we refer from journal. As you can see, after coming out from the reactor, the gas goes to the flash vessel to separate the catalyst and goes back into the reactor. Separated. Dengar tak?
Okay. Okay.
The recycle back as a feed, and the liquid coming from the gas separator goes into the gas stripping column, labeled as C1. So this column system. As propane is our byproduct, it also does not involve any reaction. So to avoid any accumulation in our recycle streams, so we decided to put membrane separator to remove the propane, and it will before recycle back into the reactor. That's for our modification. We add the membrane separator to remove the propane from our system. Thank you.
Okay, so that's all from us. Thank you. So we open for Q&A.
Okay, thank you, Group 26.
All right, thank you very much, Group 26.
Yeah,
Yes.
Okay, open for question
Now
and
we
answer.
open the session. Alan?
Okay.
Hi, this is Dr. Lim here.
Okay.
Hi, Dr.
Can you refer back to your flow sheet?
Flow sheet. Amy?
Yeah, the flow sheet.
Okay. Okay. Can you see the flow sheet?
Yeah.
Yeah, okay. Yeah.
Okay, yeah.
Um, okay. Erin,
Okay, yeah, doctor. Yes.
can you explain to me the working principle of the fresh tank?
Sorry.
Can you explain to me the working principle of fresh tank?
Okay, the flash tank, the V100. Okay.
V100?
Yeah, it is a V100. This is the flash drum, the flash tank,
Yeah.
in order to separate the raw materials and the products, which is our butyl aldehyde and also butanol.
Mhm.
So the efficiency of the separation is 95%. Yeah.
Mhm.
So it means that
Mhm.
95% of the raw material, which is the propylene, the propane, the hydrogen, and the carbon monoxide, we goes to streamline, which is the vapor outlet, while the liquid outlet will be 95% of the butanol, of the butyl aldehyde and also the butanol, will goes to stream 12 as the will leave as a liquid outlet.
Why it will be separated?
Because we want to separate the raw material, which is will be recycled back to the system.
Why?
And also,
why? How does
sorry?
this happen? How does this happen?
Why do we want to recycle back the?
No. How does this happen?
Oh, by the mean of heat, which is the boiling point of the component.
Heat? Do you provide any heat in the fresh tank?
We set the temperature inlet. So in order to separate both we check the boiling point. So to separate both, we to separate both the raw material and also the product. So we check the boiling point and see the in between the each components, the temperature of each component.
You are missing a key point here. If you want to use a fresh tank, yeah, there has to be a pressure reduction. That's the whole thing all about for the fresh tank. There must be a pressure reduction.
Oh yes, doctor.
Yes. Okay. So just
Okay,
take note of this and improve in your revised flow sheet.
Okay. Thank you, doctor. We will improve.
Okay.
Anyone else having other questions?
Okay, I would like to ask on the reaction selectivity. How you actually on the reaction selectivity, like 50% product is isobutyl, sorry, and then the other is normal, okay? Normal butyl aldehyde and isobutyl aldehyde. How you decide it is 50-50? The reaction selectivity.
Doctor, the reaction selectivity 50-50 is because from the journal we check when we use the rhodium complex, so the selectivity will be 50-50.
So it's given.
Yeah, it's given. The specific catalyst will give the 50-50 selectivity. Yeah, the 50-50 ratio. I mean. for the N and ISO.
Hello.
Hello.
Hello, dengar eh? Okay.
Yes.
So actually saya Dato' Asmani. So I have question about the distillation column T103. Okay, on top of the top distillation is vapor phase, right? So how do you condense for the stream 17?
How do we?
Stream 17. That one is you stated that one is the liquid phase, right? How do you condense the top product?
There should be a condenser.
Should be condenser, but not available in your
In
PFD
the visual,
diagram.
it's not available. But in Aspen, we have the condenser up here, doctor.
Oh, I see. Okay.
Yeah, because only
But I
in the
think
visual.
you should select the correct the instruments.
Okay, sure, doctor.
Should
We
be
will
sure,
add the
doctor.
condenser
condenser
and
up here.
reboiler there.
All
Okay.
right.
Okay.
Doctor.
Okay.
Again, for the distillation column T103, what's the temperature? The temperature for your distillation T103. Temperature.
The operating
Yes, operating temperature
is
for
140 degrees Celsius.
why you choose 140?
Because lava.
Doctor, it was calculated by using the algorithm.
The algorithm in the PD books. We follow the algorithm to find the bubble point and the dew point and decide on the temperature.
Yes. Yep.
Because your isobutanol, boiling point of isobutanol is much lower than that, right?
Yes, doctor. Isobutanol. Yep.
Yes, doctor.
Yes.
So you use that boiling point and then you calculate, you get around 140.
Yep.
Very much.
Okay. Any more questions? So one more thing. Actually, for the stream 11, what going on with the propane? Are you going to recycle or not, or just release the propane?
So okay. So doctor, after coming out from the reactor, right? So from stream 9, we are the main component in stream 9 is propane, propylene, hydrogen, and also carbon monoxide. So we are wish to recycle our raw material, which are the propylene, hydrogen, and also carbon monoxide. So before that, we have to remove propane first, because propane is an inert in our reaction and is produced as a side product. So we wish to remove this inert first before we recycle our raw material back to the mixer.
So you just remove the propane. That's all, is it?
Yeah, but the efficiency is not 100%. So it's like 95%. So there will still be 5% of propane exist in the stream 10.
So what's you going to do with that propane actually? Are you just discharge with? Are you just discharge without doing anything with the propane?
Maybe we can sell it.
Oh, okay.
Because it's propane in high purity.
Oh, okay.
Yeah.
I see.
Okay. And then the last percentage error in our manual mass balance calculation.
Okay.
We can't find the equipment for so in S1 we only can use like separator that, so the propane cannot be the main component in stream 11. So this has caused the last percentage error in our manual and simulated mass balance data.
Yep.
For stream 9, 11, and 10.
Any other question from other panels? Prof. Rosani, any comments? Any more comments and questions?
I'm just wondering, okay, you are using 95% efficiency, separation efficiency, right? Why you choose 95%? Not 100% separation efficiency. If you choose 100%, then your life will be much better, right? Because now all your it's not a pure product, right? Or and Butana, why you choose 95%?
Because 100% is not possible. It's not possible to achieve 100% separation. We can't have perfect separation. So it's
then why
only logic.
95? Why? Is there any rule of thumb? Not 90, not 98. Why you stick at 95?
Why 95? One thing.
We just set an average value because the separator normally in the industry, the separator efficiency, the good one, modified one, complicated one, maybe it's up to 90 to 99%. So we take an average on it and we take 95% because there is no perfect separation. So we take an average value between the 90 to 99.99%. So we take 95.
Okay.
Any more comments or questions? So if no comments or questions, I think we thank you very much for the team 26. Dr. Haja, you can allow the other group to join our meeting, our presentation. Okay, thank you, group 26.
Okay, thank you, Doctor.
Okay.
Thank you so
Thank
much.
you, doctor.
Okay.
Okay, thank you.
Haja boleh admin?
So do I need to remove the one thing and the group 26?
Dia orang akan keluar sendiri dah.
Sorry?
Remove pun
Dia orang
okay.
akan keluar tu.
Kalau you
They
nak
will
cepat,
now. They will now.
Okay.
you nak cepat remove je pun okay.
Remove
Kalau
the
nak
Okay.
remove
project.
pun. Okay, group 27. Okay, you can start your presentations. Please share your.
Okay, I will share screen now.
Yeah, okay, thank you very much.
Okay, I'll start now. A very good afternoon to all panels. We are from Group 27. My name is Ming Chi, and today we would like to present on the plant design project for the production of 50,000 metric tons per annum of isobutadiene from propylene. In this presentation, we will start from introduction and finally material. The three references that we obtained here are the basic background of isobutadiene. I would like to highlight that the boiling point is 64 degrees Celsius, while the melting point is negative 65.9 degrees Celsius. In terms of hazard, it is a highly flammable liquid and vapor. Also, it is harmful if swallowed and will cause serious eye irritation. As you can see here, isobutadiene is a very useful chemical and it is widely applied globally due to its various applications such as pharmaceuticals,
pesticides, antioxidants, perfume, and synthetic resins. While for the market survey, this diagram shows that Asia, Europe, and United States is the largest market of oxochemical. As compared in countries, I would like to highlight that China is the largest consumer for oxochemical, which is 30%, because they have the largest market for plasticizers where they use oxochemicals to produce plasticizers. Moving to the global demand. The global demand of isobutadiene has increased from 650,000 tons per year at 1997 to 1.11 million tons per year at 2020, showing a significant increase of 71%. While for the local demand, Asia Pacific has consumed for about 440,000 tons per year at 2017. Furthermore, for the current market price, it is priced within 1.3 to 1.6 thousand per ton of 99% isobutadiene. In order to determine the plant capacity, we have searched for possible suppliers and competitors. With the average supplier capacity, which is 470,000 metric ton per annum for propylene, and for about 130,000 metric ton per annum for syngas, and we integrated it with the average competitive capacity, which is for about 44,000. We decided to set our plant capacity to 50,000 metric ton per annum, which is 15% from our local demand.
Okay, hi, my name is Rifia Uttarinanda. I will continue with site analysis. So for site analysis, we propose our plan location at 3 locations. First, at Kerteh Terengganu. Second, at Gebeng Pahang. And last, at Pasir Gudang, Johor. For determine which location is the most suitable for our plan location, we use site rating table to determine it. The site rating table consists of several criteria from raw material supplier until political and strategic consideration, and also have a different weightage based on its importance of the criteria. And at the result, we come up for 250 for Kerteh Terengganu, 250 for Gebeng Pahang, and 170 for Pasir Gudang, Johor. So based on the highest result of our site rating table, we choose our plan location at Kerteh Terengganu. So why we choose our plan at Kerteh Terengganu? First, we will choose our land at Lot Q Polymer Park Kerteh. The available area on this lot is 24.85 acres, and the land price of this area is around 19.13 ringgit Malaysia per square feet. The other reason we choose this location because our water supplier from Semambu Water Treatment Plant is most cheaper compared to other location. And besides that, our location at Kerteh Terengganu is really near from our raw material supplier. For propylene, the supplier is Optima Olefin Centennial per head, and for the syngas, our supplier is Petronas Ammonia Plant. Other than that, the transport facility, the availability of labor, and also the clinic and fire station facility also near from this area. Next, I will continue with process selection. In order to produce isobutyraldehyde, we come up with 3 pathways and 3 reactions. The first pathway is low pressure hydroformylation of propylene with 97% conversion. The second pathway is steam methane reforming with 95% conversion. And last is direct synthesis from methanol and ethanol with 92% conversion. So let me start with pathway 1, low pressure hydroformylation of propylene. The reaction is, as you can see that above of the pathway 1, the gross profit of this reaction is 10.67 ringgit Malaysia per kilogram. And this reaction have several advantages like high activity and stability, less byproduct formation, much cleaner process, simple system, and better selectivity. But for the disadvantages, the conversion and concentration of the continuous run will be lower if we compare the batch reactor. Next, we continue with pathway 2, steam methane reforming. The gross profit is 5 ringgit per kilogram. And this reaction is the 65% until 75%. But for this reaction, the disadvantages is this reaction requires high temperature and high pressure, around 800 degrees Celsius and 25 bar. And also, if we choose this pathway, it will need 2 reactors to do the reaction. And last is pathway 3, direct synthesis from methanol and ethanol. The gross profit is 4.2 ringgit Malaysia per kilogram. And also, this reaction is only reaction that have a non-petroleum rod. And also, if we compare this reaction with the previous two reaction, this is more environmental friendly. But for this reaction, it is only available on a large scale. And also, it have too many side product and also low catalyst stability. And if the side product increase, the temperature of the reaction also will be increased. So same with the previous one, we use the same method to determine which pathway that suitable for our plant. We use process rating table with several criteria from gross profit until pressure and temperature. And at the end, we come out with the result with 298.8 for pathway 1, 171.4 for pathway 2, and 165.8 for pathway 3. So based on the highest result, we choose the pathway 1 for our plant reaction, which is low pressure hydroformylation of propylene.
Okay, hi, Assalamualaikum. My name is Zah, and I will proceed with process synthesis. So there are 5 steps in process synthesis, which I will go through one by one. So the first step is eliminate differences in molecular type. So this process is basically finding the best pathway for our reaction by considering all factors. So actually this part have been explained by my friend earlier. So I will summarize it again. So the best pathway is path 1, which is hydroformylation of propylene. It is because it is high economic potential, safe due to low pressure and temperature, and doesn't really affect the environment. So I will go to the step 2, which is distribute the chemicals. So this step requires us to calculating the overall mass balance. So here is the detail of our reactions. So here is our chemical reactions, and the temperature conditions is 80 degrees C, pressure 20 bar, and our reaction is an exothermic reaction. This reaction needs catalyst, which is rhodium-based catalyst, because this catalyst can increase the conversion to 97% of propylene and increase the selectivity of isobutadiene to 41%. There are 3 side products. For this reaction, which is N-butanol, isobutanol, and propane. So here is the overall mass balance of our reactions. And as you can see here, we are recycling back the syngas to the reactor, the unreacted syngas. So we go to the step 3, which is eliminate differences in composition. So here is our PFD with only reactor and separation unit. So I will explain the separation unit one by one. So the first separation unit that we use is phase separator, because the stream inlet containing 2 phase liquid and gas. That's why we are using phase separator. So the next separation unit is absorption tower. The usage of absorption tower instead of distillation column is because absorption tower use less energy and will reduce cost. Plus, the solvent or absorber used for this absorption process is one of our product, which is N-butadiene. So we don't have to buy a new component. If ordinary distillation column is used, we have to use high pressure or very low temperature. So after the absorption tower, we are placing the distillation column to separate N-butadiene and propane. It is because N-butadiene is a valuable product and very expensive. And for the propane, it can be used for heating element for the boiler. Next, we have a sequence of distillation column after the phase separator to separate main product and byproduct. The configuration of 3 distillation columns have been analyzed. The method of analyzing the best sequence of distillation column will be shown on the next slide. So for 3 distillation column, there are 5 possible sequence. So here are all the possible sequence. So based on analysis following heuristic, which is high priority separation last, difficult separation last, and favor equivalent split, alternative 3 are following all the heuristic. Also, alternative 3 give lower vapor flow rate based on vapor flow rate analysis. So the step 4 is eliminate differences in temperature, pressure, and phase. So we have been inserting temperature change and pressure change at the stream that require change in temperature or pressure. So based on heuristic 22, for less exothermic reaction, we have to apply external cooler or jacket vessel to maintain the temperature inside the reactor to prevent overheating. Okay, but last but not least is step 5, which is task integrations. So we have been replacing the temperature change with heater for the stream that require target temperature higher than the original one, and we replacing with cooler to the stream that the target temperature is lower than the original one. We also replacing the pressure change with valve to reduce pressure at the stream. We use pump to increase pressure at the liquid stream. We use compressor to increase pressure at gas stream. So the condition of the we also place the storage tank for the raw material and also the final product. So all of the storage have their own conditions according to their chemical properties. So next is the reactor condition, which is 20 bar and 80 degrees C. The phase spreader condition also 20 bar and 80 degrees C. So all the distillation column have their own purpose and own temperature and pressure. So the temperature and pressure of distillation column have been calculated manually by using distillation column algorithm. So the absorption tower is to separate syngas and propane. So the distillation column also. And last but not least is the mixer. So the purpose of this mixer is to mix the recycled syngas and the fresh feed syngas.
Assalamualaikum and good afternoon. My name is Muhammad Faizaim. I will continue to present about the process modification and innovation. There are three modification and innovation. The first is substitute the distillation column by the absorption tower to reduce the energy consumption. The objective we use the absorption tower is to separate the propane from the syngas before it is cycled back into the reactor. Why we need to separate a propane? It is because we want to avoid an erasure of propane from in the process. There are another method that can be used to extract to separate the propane from the syngas, which is using the extractive distillation column. But it is too expensive and do not make possible economic recovery. The second is maximize utilize our byproduct. Since we use the absorption tower, therefore, we need to use the absorber to absorb the propane from the syngas. There are several absorbers that can be used, for example, methanol, acetonitrile, and aromatic compound. But in our process, we utilize our byproduct, which is we use the N-butyl aldehyde as the absorber. So we can reduce the cost of buying the new component. The last of modification, which is we add the distillation column to purify the side product. Some of the patent do not purify the side product and they just send it into the wastewater treatment. So we have two additional distillation column, T103 and T104. At distillation T103 is to purify the isobutanol and N-butanol. At distillation column T104 is to purify the propane and N-butyl aldehyde. Next, I will present about the base case material and energy balance for manual calculation. Our production of isobutyl aldehyde is 15,000 tons per year, and our plant is operate 330 days per year. The flow rate of isobutyl aldehyde in kilogram per hour is 6,313.13. We assume that all mixture in ideal mixture behavior. To calculate the energy balance, our reference state selected at 25 degrees C, 1 bar. This is the example for manual mass balance at two-phase separator, VS101. Our assumption is 100% separation. At the stream 9, the flow rate of each component has been determined from the previous calculation. Therefore, we only have the 7 unknown at the stream 13 and stream 10. And we also have the 7 component balance. Therefore, our degree of freedom is equal to 0. So this is the molar This is the flow rate of each component that has been calculated at stream 13 and 10. Our calculation is balanced since the mass in is equal to the mass out. Next, this is the example for manual energy balance at stream 10. Our reference state for N-butylaldehyde, isobutylaldehyde, isobutanol, and butanol are in the liquid phase at 25 degrees C, 1 bar. The condition at stream 10 is at 3 degrees C, 2 bar. To calculate the enthalpy, the molar flow rate with time with the heat of formation, plus with heat of vaporization, plus with sensible heat. This is the overall mass balance. The red color is represent the mass in, which is our propylene and syngas, and the orange color is represent the mass out, which is the isobutylaldehyde and butylaldehyde, isobutanol, and propane. Based on the table, the total mass in is almost same with the total mass out. The difference is only 0.882 kilogram per hour. It is because error in decimal point in our calculation.
So now I'll share the simulation of material and energy balance. This diagram is Aspen Heiser simulation with Ing Robinson fleet package. After getting the data for the calculation from both manual and simulation calculation, we have compared it. So this is the comparison for the mass balance, and this is the comparison for energy balance. So from a table, actually all of the stream, they have percentage error less than 15, except stream 32, because Aspen Heises has included propane and N-butylaldehyde from their calculation, where we don't, because we actually assume 100% of separation for absorption power. In short, I would like to conclude that our plant capacity is 50,000 metric ton per annum, and the target site is located at Kete Terengganu with the method selected, which is hydroformylation of propylene. And by comparison, all of the stream has the percentage error less than 15%, only except stream 32. And here ends our presentation. Sorry for any delay due to internet connection, and thank you for attention.
Thank you for team 27. Okay, we open for question and answer as well as the comments from other panels. So any comments?
Before 27, can you go to your PFD? Your PFD.
PFD, okay.
Why you have to recycle your 27? Why you have to recycle your normal aldehyde, normal butyl aldehyde? Recycle to and mix with propane, and then you have to undergo distillation again.
This one is it?
Answer?
Sorry?
Can anyone answer this question? Okay, we recycle back the N-butadiene because N-butadiene is a solvent, the absorber. It helps in the absorption tower to absorb the propane from the syngas.
But you can just remove the propane without having this and butylaldehyde, right? Because you want to save the solvent, but by this and butylaldehyde, then you have extra distillation column, for example T104, right?
Because
if you don't recycle,
Because the boiling point of the propane is negative 42, if I'm not mistaken. So if we are using ordinary distillation column, we use more energy. Like,
But you can just remove propane using just having one separator rather than now you have A101 is your extraction column. Now you have extraction column, you have distillation column. Doesn't having that equipment add more cost to your production?
okay, we will check back that the cost of the absorption tower and the distillation column tower.
Right.
Yeah, just follow with Dr. Hajar question, right? If you look at like your 27, it's actually how do you decide, right? Why one you go to the storage, while the other one you want to recycle back? You know what I'm saying? Because it's the same thing, right? Your stream 41 and stream 27. It's the same component, right?
Yes.
Yeah, then why do you having a different treatment? Like one you straight away send back, you're going to sell it or whatsoever. Then the other one you want to recycle. What is the reasons?
Because earlier we used N-butyrate because earlier we separated here first, right? So this is what we will get first. Then after that, we will only use N-butyrate to absorb propane. And yeah, after that, we separate propane and N-butyrate here, which is why we were having like two streams out.
Yeah, but the treatment are different, right? Like one you finally you just store it, but the other one you decided to recycle. Then why not you just recycle back your 41 as well? If you are recycle back your 27.
Because 41 is our main product, the isobutadiene.
27 and 41, I thought it's the same. The components.
Okay.
So yeah, just why you treat them differently? They are the same thing, right? That's the point that you may want to consider.
Okay, yeah.
Okay. Any more comments, question? Prof? Prof, any comments?
Yeah, good.
Okay.
Cuba check tengok you punya yang awal-awal sekali tu apa nama you punya proses yang ada selectivity apa semua ada.
Siapa?
Kat mana yang awal tadi you punya proses selection tadi
Ini,
tu kan?
Ini ke?
Bukan. Ni. Yang ada selectivity 41% side product, right?
Yeah.
Mungkin you dah explain tapi tak dengar kot. Side product tu apa you buat dengan side product?
Because the propylene they are carried dengan hydrogen, then they will become propane. And from the isobutadiene and N-butadiene, which is our main product, they akan react with hydrogen and become butanol and isobutanol.
My question, because you punya selectivity cuma 41%, right? So that's mean, so you punya side product tu yang banyak apa?
Betul.
Apa yang you buat dengan side product tu?
41% is the selectivity.
So another 59% is the butadiene is the expensive.
Dengar, apa you buat?
We sell it, kita jual dia. Sebab lagi 59% is N-butyraldehyde. N-butyraldehyde too expensive. That's why we want to sell it.
So you jual dia punya side product juga lah kan?
Oh,
Yeah.
yes.
So
Okay.
your side product lagi mahal daripada your own product.
Itulah kata tu, kata side product
Yeah.
tu lagi banyak. Bisa dia punya selectivity cuma 41.
Tak, lagi banyak dan dia kata lagi mahal juga the price. Then why straight
Itulah
on
kata.
selling the side product rather than producing the
Itulah
Tapi
soalan itu.
tajuk.
Because this is the only way to produce isobutadiene.
Commercially lah kan.
Yalah, okey lah.
Yeah.
Okay.
How you decide the price for your isobutylaldehyde? Isobutylaldehyde. How you decide the price? Sorry.
From the we have been do our study, and I use
How?
the global price of the isobutadiene.
Because the price on the net would be 100% purity, 95% purity, 99% purity. So which price you select for your to be used in your production?
Maybe Faiz can answer. Somebody else?
Other members, I hope you can answer. Faiz or Rifki. If not, you have.
Okay, maybe for the market price we choose 99% compression because the price is around $150,000 and to $160,600 per ton with 99% conversion, 99% purity.
Okay, you choose the price with 99% purity.
Yes.
How pure is your product?
What?
How pure is your product? Because
99%.
99%.
Yes.
Because your spec is 99%.
Yeah.
Okay.
Okay, I have one question, just a short question. Stream 22 and 23, please refer to your PFD. Actually, why you have to, do you know, look at that, actually stream 22 is liquid phase, right? And there's a liquid and gas components. Why you have to increase the temperature and then suddenly you separate by using distillation? Why you have to use distillation since the component is already liquid and gas?
Sorry.
Can you explain? Anyone? Stream 22 and 23?
Stream 22
and 23.
It's a mixture actually.
Yeah, it's a mixture. Yang komponen I dengan N tu kan, dia liquid-liquid. And then you jadikan gas and liquid. And then you separate guna distillation column. Why you need distillation column? Since it's already liquid and gas.
But not all iso is in gas. It is a mixture, gas and liquid for isobutylaldehyde.
So basically, the isobutylaldehyde and butylaldehyde, they have like just tak banyak pun beza dia punya boiling point. So we have to make sure. So we have to make sure that all two component are separate. 99% separate. So because based on expert also not all isobutylate is in gas phase. They are in a mixture. That some of isobutylate is in gas and some of it is in liquid.
Oh, so that's mean butyraldehyde in liquid and gas for that one.
Yes.
Yes.
Oh,
Yes.
I see. Okay. Okay.
Yang you punya distillation T103 tu, kenapa you use temperature of 95%? 95 degrees, sorry. 95 degrees C. Temperature for distillation 103.
Feed. Yang masuk ke yang keluar?
And operating temperature for your distillation column.
Itu kami calculate by using the distillation column algorithm.
Tapi dia punya apa? Boiling point untuk you punya butanol tu above that temperature kan? What's the boiling point of your both iso and normal butanol?
Isobutanol boiling point at 2 bar 134 butanol 145 boiling point.
Okay, then you are using 95 temperature 95 degrees C.
Yes.
And the how you separate the separation process between those iso and normal butanol?
How we separate by
Separation
using
process happening at 103.
We are using distillation column because I have been calculated the volatility. Both can be separated by using distillation column.
How?
How? By using the vapor flow rate, we can get the volatility. Do you mean mechanism or?
But at 95 degrees, both normal and iso liquid, right? At 95 degrees. Both component are liquid, right?
Oh yeah.
Probably.
I think we just lepas pandang
operating condition.
Okay, I will respect the operating condition.
Okay, any more question and answer? So if no more comments and comments or questions from the panels, I think thank you for teams 27. So we will proceed to teams 28. Thank you very much, guys. Okay.
Thank you, Doctor.
Nanti masuk
Thank
ada
you,
ya.
Doctor.
Okay, thank you.
Thank you, Doctor.
Sekejap boleh admit ya.
Nah. Suara lagi tak ada ni. Tiran memang tak ada. Ada. Okay.
Hello guys, good afternoon. Okay, team 28. So you can start your presentations for 20 minutes and then after that question and answer. Okay.
Okay, Assalamualaikum and good afternoon to all panels and friends. We are from Group 28. We present on production of isobutylaldehyde. We are supervised by Dr. Nurani Osman. My name is Noazri binti Azmi and this is my teammate Interim Syati Shuhada. For my part, I will explain detail on general background of isobutylaldehyde, market survey, production capacity and site analysis. Isobutylaldehyde is infamous colorless intermediate and become important product due to demand in pesticizer, pharmaceuticals, fertilizer and many more. And it mostly manufactured as byproduct and synthesis from hydroformylation of propylene. It consists physical and chemical properties of heavy pungent smell and highly flammable. This table shows detail on physical and chemical properties of isobutylaldehyde. Next, for application, isobutylaldehyde is widely used in the plastic industry as it can be further derived into chemical like isobutanol and isobutyric acid, and it can be further react to form plasticizer. In polymer, it can be used as an intermediate to convert into hydropivaldehyde and can be formed into polymer chain. It also can be used as synthesis for collagen solvent, for latex paints. Another application is in synthetic resin and perfume. This pie chart shows global market for oxochemical. Oxochemical can be derived from hydroformylation process or oxo process to produce isobutylaldehyde and N-butylaldehyde.
This pie chart show that the Asia, Europe, and North America consist largest market for oxo chemical. They accounting 94% of world demand in 2070. For overall, world consumption of oxo chemical is expected to grow at average annual rate over 3%. For the global market, the total demand of isobutadiene in North America is around 300,000 MTA, while the total production is around 252,000 MTA, with 39,000 MTA is accounting for North America and the rest is for US. For the local market, the total demand is around 328,000, with 200,000 MTA is accounting for demand in India and the rest is for China. For total production is around 120,000 MTA, with 100,000 MTA is accounting for production in Malaysia and the rest is in China. This table shows list of isobutadiene competitors around the region North America, US, Poland, Germany, and Switzerland. For the supply, this table shows supplier for raw material to produce isobutadiene. Some of raw material needed to produce isobutadiene is propylene and synthesis gas, which is combination of carbon monoxide and hydrogen gas. For market price for isobutadiene is around $1 per kg for Germany and Malaysia and $2 per kg for Japan, Poland, and China. This market price will be used for net calculation of gross profit and economic potential. Global demand and production for isobutadiene is around 300,000 MTA and 252,000 MTA. Therefore, available capacity to produce isobutadiene in global is around 48,000 MTA, and for local demand and production is around 328,000 MTA and 120,000 MTA. Therefore, available capacity for local is around 208,000 MTA. Therefore, the production capacity will increase based on increase of market demand and supply. Our production capacity for isobutadiene is proposed at 50,000 MTA. That can be covered 25% of production capacity in Asia. The production capacity is to achieve demand of isobutadiene in global and prevent overproducing in Asia. For site analysis, we select Tanjung Lansat for isobutadiene production plant as it can be good result. A good result that could affect project in terms of sustainability and profitability. Another benefit is the product can be exported via Tanjung Lansat and Johor Port. Another benefit is the site is located near the port, therefore it can reduce cost for shipping and delivery. Okay. That's all. Thank you.
So intense literature reviews and related to the research, we have summarized 3 process pathways. The first one is the vapor phase synthesis of isobutadiene. This is a one-step synthesis which requires only methanol and ethanol to react using a complicated catalyst called vanadium titanium oxide catalyst. The operating condition of this reaction pathway is at very high temperatures at 623 Kelvin, and the reaction also has limited conversion from the reactants, and the selectivity towards isobutadiene product is very low. The major highlight of this reaction pathway is that the economic potential is at negative 0.52 ringgit per kilogram. The second process pathway is the hydroformylation of propylene using rhodium carbonyl catalyst. This is the common industrial pathway in producing N-butylaldehyde, or also known as the oxo-synthesis pathway. Commonly, industries use 2 kinds of catalysts, either cobalt carbonyl catalyst or rhodium carbonyl catalyst, depending on the motive of their production. If the industry focus more on producing N-butylaldehyde, they will use cobalt carbonyl catalyst. If they are going to produce equal amount of isobutadiene and N-butylaldehyde, they will use rhodium carbonyl catalyst. The operating condition of this pathway is very convenient at 100 degrees C and 19 atm, and industries mostly use the produced isobutyraldehyde as intermediates to further synthesis products such as alcohols and carboxylic acids. The highlight of this reaction pathway is the gross profit, which is at 10 ringgit and 4 cents per kilogram. Third pathway is the hydroformylation of propylene from steam cracking on naphtha. This reaction pathway is more or less like a prequel to process pathway 2, where the difference is on the origin of propylene. In process pathway 2, propylene is bought, while in this pathway, propylene is cracked from naphtha, from light naphtha. Other than that, the reaction equation is exactly similar to process pathway 2. The highlight of this process pathway is the gross profit, where it is at the highest point, 15 ringgit and 22 cents per kilogram. Let's make a simple comparison between the pathways. Pathway 1 has only one advantage, which is the reaction is very simple, one-step synthesis. Whereas the disadvantage is quite significant. First, the catalyst yields low isobutanol product, and the titanium catalyst, vanadium titanium oxide catalyst used is very expensive due to the complexity nature of the catalyst. It has also negative economic potential, and it is also not suitable for large-scale production. This indirectly tells us to completely reject pathway 1, and pathway 2, on the other hand, is suitable for large-scale production since it is the most common industrial pathway. It has also high economic potential, and the catalyst used, which is rhodium carbonyl catalyst, yields high isobutanol product, and it is also active at lower pressure and temperature, and at the same time, the selectivity can be controlled. The only disadvantage of this catalyst is that the catalyst is quite expensive. Process pathway 3 has the highest economic potential when compared to other process pathway, but then it also has higher operating costs due to the cracking process, which is one kind of refinery process. As we all know, refinery processes are generally complex, and therefore the operating cost is quite high. Besides, steam cracking usually yields more ethylene product than propylene product. So if propylene is quite low, it will consequently give lower product of isobutanol. A weightage table has been done to justify our selection based on several classifications such as economic potential, operating cost, the yield of catalyst, and the production, whether it can be done in large scale or not. So our marking scheme has shown that pathway 2 is selected instead of other pathways. Let's move on to the synthesis of process flow diagram. So as I said just now, we have selected the process pathway 2, which is the hydroformylation of propylene using rhodium carbonyl catalyst. So as first, as we can see here, 7,264 kilogram per hour of pure propylene is mixed with 5,640 kilogram per hour of synthetic gas at STP condition, 25 degrees C and 1 atm. And the output of this first mixer will be mixed with a recycle stream, which I will explain later. This outlet stream of this second mixer will be sent to a reactor, CSTR, operating at 100 degrees C and 19 atm. To match this operating condition of the reactor, this outlet stream of mixer will undergo temperature and pressure changes via a compressor and a cooler. Let's move on to the gas outlet stream of the reactor. The gas outlet stream has two extra side products, which is isobutanol and N-butanol. This gas outlet stream will be sent to a flash drum to completely separate between the vapor stream and the liquid stream. To match this operating condition of flash drum at 0 degrees C and 2 atm, the gas outlet stream of reactor will undergo temperature and pressure changes via a turbo expander and a cooler. The vapor stream of the flash drum will be treated as waste gas, while the liquid stream will be fed to a distillation column so that to minimize the impurities that shouldn't enter the further separation process below. So the distillate of this first distillation column will be reduced to STP condition and purged 10%, and the remaining 90% will be recycled to the mixer used early in the process. And the bottom stream of the distillation column, consisting 94% of aldehydes and 6% of alcohol, will be fed to a second distillation column to completely separate between them, so that the distillate will have aldehydes and the bottom will have alcohols. The aldehyde at this stream, distillate stream or second distillation column, will be fed to a third distillation column to purify between them, so that the isobutyraldehyde comes out as the distillate and the N-butyraldehyde comes out of the bottom stream. And the bottom stream, for the bottom stream of the second distillation column, which is alcohol stream, this will be fed into another distillation column where the isobutanol will go as the distillate stream and N-butanol will go as the bottom stream. So all four product stream will be reduced to STP condition before being stored safely in a storage tank. Thank you.
Who's the next presenter?
Jati, hold on, madam. I need to off the. Sorry, ma'am. Hold on. I can't find it. Jati, tekan mana? Sorry, guys.
Share.
Jiran, tekan yang atas tu. Dekat atas yang ada hijau tu kan.
Yang stop share.
Stop share tu. Okay.
Okay, alright. Thank you. Sorry, sir.
Okay. Good afternoon to all panels. The next part I will present is the material and energy balance. For the basis we've chosen for the calculation of mass balance is based on the demand capacity of isobutylaldehyde in the market. The target production of isobutylaldehyde in this plant is 50k metric tons per year. We assume that 1 year has 365 days and 1 day we have 24 hours. So the basis of the production of isobutylaldehyde is equivalent to 5,707.763 kilogram per hour, which also equals to 79.154 kilomole per hour of isobutylaldehyde. Next, a degree of freedom analysis is done. It shows that distillation column 3 and distillation column 4 have a 0 degree of freedoms. So it means we can obtain and solve the material balance at distillation column 3 and distillation column 4. For a distillation column, we assume the separation of the distillation column 3 and 4 is a 97%. So in the table, you can see that the temperature for the distillation column 3 and 4 for feed, top and bottom temperature, and the mole fractions for each component of isobutanol, N-butanol, isobutanol, and N-butanol. And the purity of the product we obtain is 97%. Next equipment is a reactor. At this reactor, the operating condition is 100 degrees Celsius and 90 atm. And the catalyst used is the rhodium carbonyl catalyst. In order we calculate the reactive mass balance, the information needed such as the selectivity of the catalyst of 1:1 toward the aldehyde, and the inlet of the synthesis gas in ratio is the hydrogen ratio carbon monoxide is 1:1:1, and 99% purity of the feed propane, which contain 1 weight percent of propane. And the reaction carried out in the reactor, the main reaction will be run first. So the equation such as the propylene react with CO, H2, we get the desired product, isobutylaldehyde, byproduct, and butylaldehyde, and the conversion is 0.9, which the limiting reactant among the raw material is the propylene. Next, the side reaction will run simultaneously. For the first side reactions, propylenes will react with hydrogen, we get a propane. The conversion is 0.05. For next side reaction is the isobutylaldehyde react with hydrogen, we get an isobutanol. The conversion is 0.06. And third side reaction is N-butylaldehyde react with hydrogen, we get an N-butanol. And the conversion also is 0.06. The following equipment is a flash drum. For this flash drum, the operating condition at 0 degrees Celsius and 1 atm. At the Auler-Weber flash drum, as we refer to the journals as stated below, the most of the 97% of COH2, 50% mole fractions of the propylene and propane in 4C is removed at the stream number 5. Further than that, the splitter. The operating condition at splitter is 25 degrees Celsius and 1 atm. And for calculation, 90% more of stream number 7B is recycled back to the reactor, and remaining 10% more is purged out and for further treatments. Next is the summary of mass balance. As shown in the table, at reactor and distillation column 1, the mass difference is 0.532 kilogram per hour and 0.001 kilogram per hour, which therefore our overall mass difference flow rate is 0.533 kilogram per hour.
Next part is energy balance. The equation shows to calculate the enthalpy of the species, which include the molar flow rates times with the sum of the Cp, the heat capacity, heat of formations, and heat of vaporization. This is an example at the stream number 1, which are conditioned at a room temperature and 180 atm. In stream 1, we consist of propane and propane, so the total enthalpy we obtain is 3 million kilojoules per hour based on the equation you use. The next part is process simulations.
Okay, for process simulation, this is the process flow diagram simulated by using Excel HYSYS. The simulated process flow diagram is same with the manual one, and based on this, and as seen here, all of the units are converged. This table summarizes the comparisons of mass balance between the manually calculated values and simulated values, together with the percentage errors for each stream. Uh, for mass balance, all of the streams have errors less than 15%. The maximum errors peak out at 13% for stream 7. This is due to a significant difference between the real separation condition in the simulator and the idealized separation condition during manual calculation in the first distillation column. The smaller percentage errors for the rest of the stream are due to the use of different numerical values such as molecular weight with varying decimal place and significant figures. Since the percentage error for all of the streams are less than 15%, so we conclude that the manual calculation step and the assumption made for mass balance are acceptable. This is comparison of energy balance for the manual values and simulated values. Unlike mass balance calculation, errors are generally much more significant during energy balance computation due to the difference in the steady state and other inaccurate thermodynamic assumptions. As we can see here, there are 6 highlighted streams that have more than 15% errors. This is due to the variance in heat capacity values being used for each component in a stream during manual calculation and simulated computation. It is also due to the imperfect separation in the distillation column, thus resulting in a slightly different composition in the distillate and bottom stream. As a result of this different mass flow rate for both manual and simulation, there are deviations in the energy balance. Then I will proceed with the process modification and innovation. This is the common industrial pattern of butadiene production by this journal in 2014. Compared with this process flow diagram, there are several modifications have been made. The first modification is negation of 2-ethylhexanol as side product. Generally, in industry, they mostly use cobalt carbonate catalyst with selectivity of 10:1 towards production of N-butadiene to isobutadiene. The excess amount of N-butadiene produced will enhance the conversion of 2-ethylhexanol as byproduct. But in our current proposed process flow, we use a different catalyst, which is a rhodium carbonate with selectivity of 1:1. This will result in a less N-butadiene production. Hence, 2-ethylhexanol is produced in almost a negligible amount. The second modification is maximizing the process performance by introducing purge stream. As you can see here in the pattern, the distillate of both separator and column are merged and then recycled to the feed without being purged. But in our revised process flow, propylene feed is purged at about 10% of the impurities before being recycled to the reactor. This is mainly to avoid these impurities from being accumulated, which will make the attainment of steady state impossible. Lastly, usage of rhodium catalyst in batch. In continuous hydroformylation process, industries commonly recycle cobalt catalyst back to reactor in order to avoid unnecessary wastage of catalyst. However, we use rhodium catalyst, which is difficult to be separated from product stream due to low immiscibility.
Hence, catalyst is not encouraged to be recycled. So we use rhodium catalyst in flash usage. With that, I end our presentation with thank you.
Okay, thank you, team 28, right? Okay, okay. So now we open for question and answer from the panels.
For your site analysis, how you decide on the site for your plant?
We use a weightage method for decide site selection.
Can you show us? Because I don't see any table of.
Oh, I don't put the table. This, the table on slide shows only the data for each site.
So you do have the table of justification.
Yes.
Yeah.
Yeah.
Right. And okay, for your PhD, why you have to have two mixer, mix 100 and mix 101? Why don't the recycle one just go into the mix 100 rather than having another one mix 101? Can you go to show your PhD?
Yes. This is the one, right, doctor? These
On the
two.
left, yes, this one.
Yes. You have to. Why not the recycle one just enter the mix 100 rather than having another mixer?
Actually, doctor, we have tried that kind of simulation too, but then the simulation doesn't converge. It's like we did that in manual design, but then when we tried that similar design to do it in simulation, it doesn't converge. So that's why we have choose to use a separate stream, separate mixers.
Then you have another extra equipment, right?
Yes, doctor. I think we will improvise more on this. Actually, we'll take note on this.
Saya rasa awak sepatutnya tak ikut simulations. You punya selalunya yang betul yang base kepada manual.
Okay, doctor.
Alright. Okay.
Semacam
so macam tak ada point you nak have another because process is quite straightforward, right? So just masukkan je lah dalam your mix 100 tu.
Right, noted.
Okay, my question is for the equipment CRV 100, that is reactor, right?
Yes, doctor.
There's a bottom. Is there any bottom product? Why you written that ignore? What do you mean by ignore?
No,
Actually, yeah.
it's zero kilogram per hour. So it's a no outlet. So we just ignore because it's no out products coming out.
There should be no outlet product. Why you still have a arrow for the outlet product?
No, actually we refer to expert. For reactor, there are two outlets, which is the top one is for vapor and the bottom one is liquid. So since all our products are vapor, so the bottom one is zero.
But this one you draw manually, right? Not using the aspen, right? Yes, manually. So I don't think you have to include this one, this stream.
Okay, doctor.
So that means just one outlet.
Yes, because there's nothing here. Okay.
This is Dr. Lim here. I'd like to comment on your flow sheet as well. I think your flow sheet is rather unusual. Typically we don't use a triangle, right? To label the stream and also the condition, right? The triangle. And also the way how you do the numbering. like A, B, C. I understand like you're trying to say it's one stream, right? But try to use a more typical way to represent all your unit operations. And also the labeling. Can you take note of that?
Yeah.
I would like to ask about your V100. I noticed that there's a drastic temperature. Why do you need 0 degrees Celsius for that distribution column? How do you determine the temperature?
Okay, sir. The gas outlet, the outlet.
Can you louder? I can't really hear it.
Okay, so the gas outlet stream of this reactor, right? It consists of side products and also main products. So side products, I seen isobutanol and butanol and propylene, carbon monoxide, hydrogen, and propane. So as we see, 4 components have negative boiling points, which are propylene, propane, carbon monoxide, and hydrogen. So all these are negative boiling points. So if we set the temperature at 0 degrees Celsius, that temperature is perfect to separate between the vapor stream, which is propylene, carbon monoxide, propane, and hydrogen, and the liquid stream, which are our product, which is isobutyraldehyde, N-butyraldehyde, isobutanol, and N-butanol. Basically, the boiling point is, there are several boiling points that are negative and there are boiling points that are positive. So we choose 0 as the benchmark to separate between them.
Okay, because it's quite a big temperature difference. Before that, it's like you have like about 700 right, degrees Celsius.
Yes,
am I right?
Yes, sir. Yes, sir.
Yes. Drop all the way to 0 degrees Celsius.
Yeah.
But I think if you use 25 degree, it still works, right? Rather than 0 degree. 25, it still can separate room temperature. Because when you lower the temperature, it means you increase the cost.
Maybe if 25 degrees Celsius, maybe the component, the flow rate of the 4 vapor will be less in the distillate. The flow rate will be, I mean the separation.
Do you come up with
your distillation column temperature? Is it really 0 or what?
So do you mean the vapor, the flash drum V100?
Yes.
Oh, that's okay. That why it's a fresh drum, is it?
Yes, sir.
If there's a fresh drum, why there's no pressure reduction?
No, doctor, there is a pressure reduction. Yeah, K101 beside the CRV 100, right? There is a turbo expander K101. So that turbo
No,
expander.
which one you're talking about? V. We are talking about V100, right? Is it a distillation column or is it what? It's a fresh tank.
Yes, doctor, it's a flash drum. So CRV 100 is CSTR. It's a reactor. So CRV, the outlet stream of CRV 100, which is stream 4A, will undergo pressure reduction first at K101. So K101 is a turbo expander. So the pressure will be reduced there, and then the following stream will undergo temperature reduction in a cooler. So it's a two process pathway. I mean, two process.
I thought normally when you do the fresh tank, you should be the pressure should be dropped within the tank itself.
Oh. Okay, doctor.
Huh?
Okay, doctor. We
No?
will take note of this also.
So yeah, be careful of your frost sheet.
Okay, doctor.
And some of your symbol, right, is rather weird as well, like the VLV 100. What is that actually? The one that between 12A and 12B.
Pressure reducing valve, TRV. It's a pressure reducing valve, doctor. PRV.
I think you should include in your PFD is the for the full name for each equipment. You didn't define all the symbol actually, isn't it?
Yes, doctor.
Mm.
Yeah.
And I don't know what's the
And
equipment. Yeah, I don't know what the equipment
you
for
should,
T is. Okay, junction.
just trying to highlight the same thing. At least you try to use a typical simple, right? Try to redraw this, right now it's like it very messy, you know, with all the triangle or those things. Hard to understand.
Okay,
And
doctor.
triangle, yeah.
Okay, you done, Jinshuan? Dr. Jinshuan?
Yeah. Okay.
Okay, so I'm wondering, your stream 3C, from 3C you hit up to 280. Lepas tu you lower balik kepada 100 degree C. What's the purpose of doing that? From room temperature, you heat up to 280, and after that you lower the temperature to 100 degrees C. From 3C to 3D, right? 3C,
Before
3D.
the reactor, CRV
Yes, before
100. Yeah.
entering the reactor. What's the purpose of increasing and decreasing the temperature?
Doctor, for after mixer, we enter the compressor, so the temperature is increased. So we need a cooler to decrease the temperature before we enter the reactor.
But your 3B is 25 degrees out from mixer? Am I right?
Out of mixer is 25. After we need to increase the pressure, the temperature is increased until 280. So that's why we need a cooler to decrease the temperature back.
Or the purpose is to increase the temperature, the pressure, sorry.
Because the condition for the reactor is 19 atm. We require the temperature at 19 atm. That's why we increase the pressure first. So after the increase the pressure, the temperature also increase. So we need to cool down the temperature. That's why we got a compressor and a cooler.
Okay.
Okay. Any more comments or questions?
I have your distillation column that operating at minus 40. Mana? Which distillation column?
This one, 7A.
Yang tu distillate.
Why minus 40?
Tak, Doctor, that one is the distillate of the first distillation column. The distillate stream.
Oh, so
The
your distillation operating condition is?
0 degrees C at stream 6.
Okay, also using 0 degrees C.
Yes, the same condition with the flash drum, yeah.
Zero degrees C. Why? Why 0 degrees C?
Actually, Doctor, the purpose of the first distillation column, right, is the purpose is similar to the flash drum, which is to separate the 4 negative boiling point components, which is propylene, CO, propane, and hydrogen. The purpose is similar with the flash drum. So since the flash drum efficiency is not good enough, we have added on another distillation column to separate them. So only then we will purge and then recycle back to the mixer. So the bottom stream of the distillation column only, which consists of 4 products, will be undergoing the separation process.
Why not having buang je apa you punya flash drum dan ada distillation column je?
Doctor, because our limiting reactor is propylene, so we aim only propylene to recycle back to our reactor. So we remove the CO and hydrogen at the flash drum.
Okay.
Okay. Any more comments, questions? Okay, so if no comments or questions.
One
One more.
more.
Okay, aja.
Sorry,
Okay.
sorry. So you using 365 days for your operating apa? Plan operating days. 365 hari per year. So no allocation for maintenance, everything. Am I right?
Yeah.
Yeah, if not mistaken, Dr. Jaishu, you can correct me. Dalam you punya plan design one, dia dah stated kan, the assumption should be 330. The operating.
Ada some assumption, I think. Yeah, there's some assumption need to be taken.
So macam mana? They supposed to use 330 or it's okay kalau use 365? I think it's kind of impossible kot to use.
Azrin, boleh jawab? Awak tak ada jawab soalan lagi.
Boleh je adjust, I think. Kalau mereka boleh adjust. Kalau boleh, bagus adjust. Or they can scale down. It's just a matter of scaling, right?
It's
or
more
method
feasible, right?
Yeah.
So macam mana? The team members?
No, it's either you do it here or you can do a scaling later on. I mean, just to play around with the math. If they want to remain the calculation here, they can, but later on they just need to scale down the value. Because right now they're based on 365, right? Yeah, they can scale down. If they don't want to redo the simulation or the calculation, they just need to have a table or whatsoever to scale down the value accordingly. I mean, if they want to save the effort.
Okay then. So it will be more feasible lah kalau using 330. Okay.
Yeah.
Alright, so that's all.
Okay. Anything else? Okay, if no comments or questions from the panels, thank you, group 28. Okay. So thank you very much.
Thank you, Doctor.
Okay. Aja boleh masukkan.
Okay. Syafiq tak? Syafiq nak? Is Syafiq here?
Belum masuk lagi.
Masuk, okay.
1, 2, 3. Lagi seorang.
Alright, okay.
Okay. Interim, you can leave meeting room. Okay. Later you can join. Okay. Okay, Shafiq and Tan Chacha, can you turn on your video?
Oh, okay.
Okay. So hello guys. You can share your PowerPoints and you can start your presentations for 20 minutes.
Start, Doctor?
Yes, you can start. Okay.
Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and thank you to all panelists for being here today for us. I would like to present to you our plan design project which production of 50,000 ton per year isobutadiene IBA from propylene. Before that, I would like to introduce our plant manager, which is Dr. Noafiza Yunus. Next. So this is our presentation outline. Next. So for the introduction for our product, isobutyric is a colorless, highly flammable, and exists as liquid at room temperature. IBA serves as an intermediate for chemical industry, an important component in producing paint, lubricant, coating, resin, and plasticizer. So for the physical properties, the molecular weight is 72.11 gram per mole, and the melting point is negative 66 degrees C, and the boiling point is 64.33 degrees C. The density is 790 kilogram meter cube. For the chemical properties, it is very slightly soluble in water. It is miscible with almost all common organic solvent. And the safety and health hazard, it is highly flammable liquid. Upon contact with water, it will produce a vapor which cause irritating to eyes, nose, and throat, and difficult breathing if inhaled. Liquid itself can cause irritation to our body. So for the application of IBA, it serves as an intermediate raw material of isobutanol, isobutadiene diurea IBDU, neopentyl glycol MPG, and isobutyric acid. Next. So for the market survey and outlook, the market survey of IBA is widely used for neopentyl glycol MPG production. So the MPG synthesis by hydrolyzation reaction of IBA, formaldehyde, and benzyl-trimethylammonium hydroxide with presence of amine as the catalyst. The ratio MPG to IBA by mole is 1 to 1.1. It's about 0.7 kilogram IBA is required to produce 1 kilogram of MPG. So for the global demand of IBA, the graph shows that each region shows the increment of NPG demand from 2015 to 2019, and the total NPG demand globally is about 800,000 tons per year. This shows the global capacity of IBA. It's also from 2015 to 2019. It shows that the global capacity production of PG is about 890,000 tons per year. So for the local outlook of IBA, Asia Pacific supply about 33% of global MPG production. From the global capacity of 890,000 tons per year MPG, Asia Pacific supply about 300,000 tons per year of MPG. The required amount of IBA to support MPG production is 210,000 tons per year. From the 0.7 kilogram of IBA need to produce 1 kilogram of MPG. So these are our list of competitors from China mostly, and their production is from 33,000 tons per year to 10,000 tons per year. Next. So this is market price of isobutyric from 2003 is $4.84 per kilogram, and for 2016 is $5.25 dollar per kilogram. So this shows that the increasing demand of IBA has also increased the market value. So this the summary of the outlook. So from the global of MPG production is 890,000 tons per year, and the specific capacity of MPG production is 300,000 tons per year. So the required IBA production for SFSP is 210,000 tons per year. So the existing capacity of IBA production is about 120,000 tons per year. So the demand to be fulfilled is 90,000 tons per year. So our chemical plant produce about 50,000 tons per year. This production shows less than the demand due to create market for our product. Next. So we go to the site analysis. So we have choose three site location: Pasir Gudang from Johor, Gebeng in Pahang, and Kerteh in Terengganu. We have selected Pasir Gudang as our site due to meet the criteria that we need. So first one is raw material. Our plant located at many neighbor supplier, so it's beneficial in terms of networking and continuity of supplying. It also can reduce the cost of delivering raw material and labor costs for the manufacturing. So the second one is the market availability. It's around with the many company which producing product using isobutyric such as Nippon Paint. They produce paint and coating. And also for the transportation, it's located close to the ports, and the ports is free trade zone, which lead to reducing tariff barriers, and also near to well-maintained roads, highway, and railway transport. For the fourth one, local community, there are many residential area nearby within 8 kilometers in distance from the site. And also it is nearby hospital, which is very important in managing critical situation. And lastly is the availability of labor. There are many high potential training institute such as UTM, UTHM, and UTM to provide training for prospective professional and to upgrade the skills of the worker. This table shows how we grade our site selection. So Pasir Gudang shows the highest mark compared to the others. That's all for me.
So I will proceed with the process selection. So we have 3 possible pathways for our production of isobutyraldehyde. So for the process 1 is the hydroformylation, which also named as also process in the industrial. So this reaction of carbon monoxide and hydrogen, also called as syngas, with olefinic substrate to form linear and brush aldehyde with additional carbon atom relative to the starting olefin. So for the second process, which is the oxidation of isobutanol into isobutyraldehyde. So the isobutanol can be partially oxidized or dehydrogenated by suitable catalyst to form isobutyraldehyde. So for the last process, which is single step synthesis of isobutanol from methanol and ethanol. So the IBA can be synthesized in one step from methanol and ethanol using copper oxide, zinc oxide, aluminum oxide catalyst with the formation of side product which are formaldehyde and also acetaldehyde. So this is the economic potential for process 1, which is the hydroformylation. So from the overall equation, we get the economic potential for the production is ringgit Malaysia 8.03 cent for every kg of isobutyraldehyde. So for the second process, the economic potential that we get is 5 ringgit and 39 cent for every kg of IBA. And the last single step analysis, we will get 2 ringgit and 97 cent for every kg of IBA produced. So from the process, we have also strength and weaknesses. The strength for the first route is that it has high and stable activity of rhodium catalyst. The overall conversion of 93% from the propene, and it has high reaction rate, which can contribute to less energy consumption. So it also will be easy to separate and to purify the products. However, the weaknesses is that the rhodium catalyst is expensive, and we will be operating the plant at high operating pressure, which is 35 bar. So for the second route, we also have high conversion of 95% and selectivity of 98%. And we also use a good catalyst, which is copper oxide, that will mostly oxidize the reactant into aldehyde only. However, it will operate in high operating temperature, and it's less commercial process to reoxidize the isobutanol back to isobutyraldehyde. As we mentioned before, isobutyraldehyde will be used to form isobutanol, so it's less commercial to convert it back to the IBA. So for the last route, which is high selectivity of 90%, so overall conversion for the process is 99%, and IBA will be produced as the main product, and also less side product will be produced. However, it will be having a very complex process since the mechanism will include dehydrogenation, condensation, methanol addition, and also dehydration in the single step process, and it will operate in high temperature. So from the strength and weaknesses and also the economic potential, we have the justification using the weightage. So the highest weightage is using the first route. So this is the route that we use to produce our IBA. Then for the process synthesis, using the 5 key synthesis process. So here is our process flow diagram that we obtained. So here the raw material will be feed, which is this is the place for syngas, and this is the feed for propane. So from this, it will reacted at this reactor. So here we will separate the product and the unreacted raw material. So then our final product will be separated using distillation column. So for the main equipment, first the reactor. So the reaction will occur at plug flow reactor. So the reaction at 35 bar and 300 degrees C. The catalyst we use is rhodium copper oxide in nanoparticle size 8 by the toluene solution. Next, we will use vapor liquid separator, in this case demister pad. So the demister pad we will use to strictly separate between the solution, catalyst solution, and also our product stream. So the catalyst will exit as liquid stream here, and the product stream will exit here as a gas stream. Next, we will use separation process, which is flash drum. So here the flash drum will operate at 55 degrees C, 1 bar. The flash drum will separate the unreacted raw material and the product stream. So the product stream will consist of
isobutyraldehyde, N-butyraldehyde, isobutanol, and N-butanol. So the unreacted material is propene, propane, and also syngas. Syngas is carbon monoxide and also hydrogen. So the unreacted raw material will be recycled back to the feed stream, and the product stream will flow to distillation column to be separated. So for the first distillation column, we will separate between the IBA-NBA and IBO-NBO. So the IBA and NBA will be exit as distillate, and the IBO-NBO will exit as bottom. So this IBA and NBA will flow to the second distillation column, which is T101. So the separation will produce IBA at distillate with 98 composition and NBA at bottom also with 98 composition. And after that, the NBO and IBO will go to the last distillation column, which is T102. So it also separate the IBO as distillate with 98 composition and NBO as bottom with 98 composition.
So, good afternoon all, I'm Chacha, and now I will proceed to our manual mass and energy balance. So our basis for the mass balance is 50,000 tons of the isobutyraldehyde per year, and we assume that the plant will be operated for 330 days and 24 hours per day. Therefore, we can get the value of the 87.55 of kilomole per hour of isobutyraldehyde. Next, this is the overall mass balance of the production. The red color box represents the raw material, while the blue color box represents the product. So from here, we can conclude that the overall mass is balanced for the input and output. Only the difference of the 1.67 kilogram per hour is due to the error of the decimal point calculation. So next, we will see the mass balance for each unit operation. Firstly, in our left-hand side is a mixer M100. This mixer is used to mix the fish feed from stream 1, 2, and recycle stream 31 to produce stream 3. From here, we can see that the total mass in is equal to the total mass out. In our right-hand side is the mixer M101, which is used to mix the feed toluene and the recycled toluene back to the reactor. And here the mass difference for input and output is 0. Next, this is a reactor. The equation involved and the conversion for each equation is shown in the slide. And from the table, we can see that the total input is equal to the total output. Next, this is a vapor liquid separator, this demister pack, which is used to separate the liquid catalyst from the gaseous product. So we assume that there is 100% separation between the vapor and liquid, and the mass difference calculated between the input and output is 0. Next, for the splitter S100, 25% of the liquid toluene with the catalyst is pushed out, while for the splitter S101, 50% of the gas is pushed out. There is no mass balance calculated for input and output for both of the splitter. So next, for the flash drum also show that the mass is balanced. Next, for the distillation column T100, which is used to separate the isobutyraldehyde, butyraldehyde, butanol, and isobutanol. From here, we can see that the mass difference is 0. Next, for the distillation column T101, which is used to separate the isobutyraldehyde and the butyraldehyde. Here, the mass input is same as the mass output. So next, for the distillation column T102, which is used to separate the isobutanol and butanol, and the mass is balanced also. So next, we will proceed with the manual energy balance. So we calculate the heat transfer based on the MCP delta T plus heat of formation. If the heat transfer involves the changes in phase, then the equation will be the sum of the heat of formation, MCP delta T, and heat of vaporization. So next, these are some assumptions made in the energy balance calculation. In the assumption, we neglect the effect of the pressure change on the heat enthalpy if the pressure changes is less than D at the end. We also neglect the enthalpy of the mixing and enthalpy of solution, and the enthalpy is calculated based on the individual components only. And most importantly, all the stream and the equipment is assumed to operate at steady state condition. So next. This is a summary of the energy value for each column. The positive value in the energy balance column indicate heat absorbed, while the negative value means heat release. So next. This is a summary also. Next. Okay. Next. Joe, that's all for my part. Joe.
Tajudin, it's your turn.
Okay. Hi all and good evening. So I am Muhammad Nur Tajuddin. So I will continue with Aspen High Seas simulation. So as we can see here, this is our simulated PFD. So for the fluid package, we use Penn Robinson. And this is the formula we use to determine the absolute relative deviation. So this is for the mass balance. And this also for mass balance. So as we can see here, the overall stream give a lower relative deviation, which is less than 15%. So it is considered as acceptable. And that is for energy balance. As we can see here, there are some few streams as highlighted in red, give higher relative deviation, which is greater than 15%. Also for these few streams. And our justification is, in simulation, the pressure difference, the pressure changes were considered in its calculation. And the most important thing, instead of difference in temperature, the constant of heat capacity of each component might be quite different from manual calculation, especially for NBO and IBO. And the last part is our innovation or process modification. Commercially, this process, hydroformylation, focused on production of NBA, and this will cause low conversion of and selectivity for our desired product, which is IBA. And they use homogeneous catalyst, which make them trouble to separate the catalyst from the reaction mixture and catalyst recycling. And for our modification, we use catalyst rhodium copper oxide with nanoparticle size with the aid of solvent toluene, so that the combination will make heterogeneous catalyst and make them recyclable and easy to separate from reaction mixture. Therefore, our catalyst can be reused many times without loss in activity and selectivity. And this combination also will produce high amount of IBA with ratio to NBA 6:4. So that's all from us. Thank you.
Okay, thank you guys. Now we open for question and answer as well as comment from the panels. Just now you stated that you just purchased toluene and catalyst, isn't it?
Sorry?
Just now you mentioned that you just purchased the toluene and catalyst, isn't it?
For the first separation, kita akan separatekan, sorry, I buka.
Yang ni, tadi tu.
Fine.
No, next.
Next.
Next. This one. It's purge out. Why you just purge out? No recycle that catalyst.
Sebab kalau, okay.
You say.
Yeah, boleh.
You say first.
Because the catalyst, we have constant flow of the catalyst, which is 80 kilogram per hour. So if we continuously only recycle the catalyst, it will generate more catalyst in the reactor.
So apa yang you buat dengan toluene and catalyst ni selepas you purge out? Apa yang you buat? You buang macam tu je ke?
Sorry.
The toluene and catalyst you purge out kan? You apa you buat? You just buang macam tu je ke?
Ya, buang macam tu je.
Kenapa you?
Kerana
It's toluene, right? So
yeah, because actually our catalyst is inside the toluene, right? And then we scale like after recycling of the catalyst many times, the efficiency will be reduced.
Okay.
That's why we need to push them out.
Okay, thanks.
Just a suggestion, right? Make sure you recover the heat when you're pushing out the stream, because you can see the heat is actually very high, right? So later on when you do the treatment, improvement, make sure you recover the heat. It's about 300 degrees Celsius, right?
Okay.
I'm looking at your mass balance, manual mass balance, okay, at the flow sheet document provided.
Okay.
Can you explain to me on the V100?
V100. This one.
Yeah. I think there's some mistake in the document, in the provided. You see the toluene mentioned here is 20, right? The input for stream 5, stream number 5. I'm referring to the document, PFD document, the PDF document that you sent to us. Did you see it? Stream number 5.
Stream number 5.
Yeah, the toluene. What is the number?
80.
In the document.
Doctor,
yeah.
I think it just mistake because before this we decide to put 20 kg per hour for toluene, but after that we changed to 80 kg per hour, but unfortunately we forgot to adjust the PFD that we gave to Fenner. So
Okay, but your calculation is so correct based on 80?
Yeah.
Your calculation is correct, it's just
Typo.
okay, so make sure you correct it.
Okay.
Boleh saya tengok you punya process flow diagram PFD?
Process flow diagram.
Okey. Cuba saya cuma nak tanya itu aja. Ya, dalam you punya proses ni, you tak ada yang you akan discharge sebagai wastewater ataupun sebagai emission, tak ada ya?
Ada yang kat S1012
kat mana?
atas. S101 ya, sama.
Kalau yang discharge effluent?
So here kita akan we will push the syngas and also some propane and propane. So
you push ke mana?
Yang this one.
Tak, you push ke mana? Ke mana you push dia? Push ke mana? Bila you kata you push kan, you push ke mana?
Actually, this one later on will undergo like wastewater treatment like that lah. So mungkin dia.
So kalau yang push tu wastewater ke emission?
Emission.
So you tak ada mass balance kat situ. What is the concentration, berapa quantity, dan macam mana you nak design you punya emission system later on kalau you tak buat mass balance.
Kita ada mass balance dekat S101.
Satu ada.
Ada.
Yang wastewater?
Sebab kita yang this one ke?
Yalah, whatever lah yang mana.
Ada. Kami semua stream kami ada buat mass balance.
Yalah, because mass balance. Tapi kalau tengok kat sini, macam you letak satu arrow keluar je. It doesn't go to any equipment. Betul tak?
Betul.
So what the meaning there? You just push everything to the environment macam tu. Is it allowed? They must have equipment. There must be ada unit operation kat situ, betul?
Yes.
Betul tak?
Betul.
Then at least, itu saya kata at least what kind of equipment yang you akan because kalau you ada yang lain, distillation column, reactor, all the specification, right? So that's also part of your process. You tak boleh kata simply benda tu you push macam tu aja tanpa ada dia punya treatment ke apa ke. So kalau you kata ada treatment pun, that mean that must have a unit kat situ. Dia bukan just arrow. Kalau arrow keluar macam tu aja, maksudnya apa meaning dia maksudnya? Ada treatment ke tidak?
Ada.
Tak ada. Betul tak?
Betul.
Sebab tu saya kata semua group saya rasa sama. Tak, maksudnya you punya PFD tak complete. Maksudnya boleh tak you buat plan mass balance, energy balance without taking into consideration you punya treatment of the gas yang you nak push ataupun yang you nak discharge sebagai wastewater. Mana dia punya unit dia. Kan? Kalau yang lain you ada specification, valve, pump apa semua ada. That's very large equipment, bukannya kecil-kecil. Okay, so make sure you include yang tu.
Okay.
Okay. So untuk your innovation, other than you change the catalyst, ada innovation lain tak, especially on the PFD?
Oh, tak ada. Hanya yang catalyst je.
So you use the exact PFD as the ni lah, establish lah.
Almost same lah.
Oh, same. You just change the catalyst.
Yes.
Doctor. Doctor?
Yeah.
Maybe I can add something about the innovation. Actually, the commercial one, it does not use the flash drum, but it use stripping column, so that the syngas will fit into the stripping column first, and it will recycle back to the reactor, and so on. But for us to separate our product in liquid form, it is impossible for us to make the syngas into liquid. So that's why we use flash drum instead of stripping column.
Okay, so ada another improvement lah on your PFD. Okay. It's important tu je, next time you kena highlight.
Okay.
Okay, I have one question actually for stream 7, 11 and 10. Which arrow actually is that direction actually? Saya tak nampak ke mixture ke mana? Ke mixer, ke reactor ke?
7, 11 and 10.
You punya PFD.
7 is the recycle toluene yang kita separate from the demister pad. So 7 will go to the mixer. 10 is the stream after the toluene we change the temperature, the pressure here. So it will also go to the mixer. So we will mix the heat toluene and also the recycled toluene here. So the 11 ialah mixture.
So masuk ke reactor. Okay. Sebab you punya PFD ni tak lengkap, tak ada arrow dia. Okey, nanti betulkan ya.
Okay.
Okay, any more comments and questions from the panels? Okay, so kalau tak ada aja?
Tak ada.
Tak ada. Okay. Junctions, any comments? Tak ada.
No.
Prof? Is it that's all? Tak ada. Okay, so thank you team 26 29. So just day kita akan allow semua team masuk dalam meeting room ni lah.
Meeting room ni lah.
Meeting room. Okay. So Haja boleh.
Belum ada yang request ni.
Tak ada yang request.
Tak ada.
Dah ada dah?
Belum.
Tak ada.
Lapan je kita je.
Tajudin ke Caca boleh minta kawan awak masuk.
Okay.
Sebab saya dah inform dalam grup. Tak ada. Ke semua kawan awak dah tak ni, dah tak online. saya dah inform semalam kan.
Mana tak? Ke dia ada problem? Saya tak ada.
Sebab dia tak ada saya. Tapi kalau tak boleh tak apalah kot kan. Okey. Tak ada ya? Tak ada. Okey. Kalau tak ada tak apalah kot. Okay, so nanti you just forward message ni kepada you punya kawan lah, ataupun nanti saya tulis kat grup. So sila betulkan komen ni saya akan kumpulkan daripada setiap panel. Okay, so kemudian saya akan forward kepada coordinator lah. Coordinator akan kasih dekat awak semua lah. Ya?
Doktor.
Ya?
Kita tengah tunggu host admit.
Admit aja. Tak ada dekat atas tu.
Tak appear? Ni ke? Kat mana?
Admit. Atas tu. Awak kena tekan admit macam tadi.
Tak keluar. Tadi kan dia appear. Dia orang request tu ni. Request ni tak appear.
Tak appear ya?
Tak nampak participant. Dia tak ada
Cuba buka participant punya tu, mungkin dia keluar kat situ.
Dekat participant.
Kat participant tu lah. Tak ada. Just 8 orang je. Kan biasa dia akan dekat participant tu kan dia orang request.
Okey, tak apalah, tak apa.
Ini dia orang semua kata okey.
Okey, tapi tak masuk. Okey, tak apalah, tak apa. Mungkin ada masalah kot connection. Okey, just sampaikan itu yang saya kata tadi. kemudian saya rekod juga video presentation ni. Okay, kemudian saya akan upload dekat YouTube lah. Saya akan kasih link nanti later. Okay. And then untuk semua panel juga saya harap nanti boleh hantar komen tu kepada saya lah melalui email. Komen.
Ya,
By email. Tak kisahlah. Nanti saya
Maksud
tanya
few
koordinator.
days pun boleh. Bukan
Few days lah. Saya rasa few days ke okey kot. Okay. So itu je lah saya rasa untuk hari ni. Kalau mungkin ada komen daripada panel lain, boleh lah. Okay. So kalau tak ada apa-apa, terima kasih semua. Maaf lah dengan internet connection and mungkin ini first time kita buat online kan. Okay, saya harap everything is okay lah. Okay. So thank you very much. Okay. Terima kasih semua. Okay.
Terima kasih doktor. Terima kasih doktor.
Terima kasih juga kepada panel yang cuba untuk ni lah.
Kejap ni.
Tu saya pun panas ni. Tukar bilik tadi, internet connection. Okay. Terima kasih Prof. Okay. Terima kasih Dr. Hajar dan terima kasih Dr. Jeng Shun. Okay. Terima kasih.
Okay.
Bye bye.
Okay.
Thank you, Doctor.
Thank you. Okay. Salam.